and welcome back to my videos for General Chemistry 1. To start out today, imagine you're a brave and charming international spy. Unfortunately, because you're such a good spy, someone has tried to poison you. As a result, you've swallowed a small amount of plutonium, which is very toxic. It's important to get it out of your body as soon as possible, but unfortunately it can lodge into your bone marrow instead of being excreted. What can we do to remove it from your body? In real life, one way we can cause it to be excreted is by giving the victim a dose of this ion, which has the long name ethylene diamine tetraacetate, or EDTA. In today's video, you'll learn why ingesting this ion is a good way to get plutonium out of your body. And to understand that, we'll need to continue our discussion of Lewis dot structures and apply it to bigger molecules than the ones we've looked at so far. Take nitric acid, for example. As you hopefully learned way back in video 5, nitric acid has the formula HNO3. What will be its Lewis dot structure? This one is more difficult than the Lewis structures we saw in the last video. Is the hydrogen attached to the nitrogen or to one of the oxygens? And are the oxygens attached to each other or to the nitrogen? For larger compounds like this one, there's a method we can use to get the Lewis dot structure. There are 6 steps in this process. The first thing we need to do is to find the total number of valence electrons for the elements in the compound. Let's try it for these 4 compounds and ions. In the first compound, which is our nitric acid, the periodic table tells us that the hydrogen has 1 valence electron, the nitrogen has 5, and each oxygen has 6. There are 3 oxygens, so the molecule has a total of 24 valence electrons. In this second molecule, which is acetylene, each carbon has 4 valence electrons and each hydrogen has 1, for a total of 10 electrons. In the third example, there are 5 for the nitrogen and 1 for each hydrogen, for a total of 9 electrons. But wait, in this example, our molecule is an ammonium ion with a charge of +1. That means it has had an electron removed. So instead of 9 electrons, we only have 8. The fourth molecule is a carbonate ion. In this one, the carbon has 4 valence electrons, and each oxygen has 6, for a total of 22. But remember, this is an ion. It has a charge of -2, so we need to add 2 electrons to our total, which gives us 24. So now we know how many valence electrons are in our molecule. You might remember that in a previous video, I told you that the valence electrons are the ones that form bonds when atoms are connected together. So that's what we'll do in step 2. We'll use the valence electrons to sketch out the bonds between the atoms in these molecules. To do that, we'll need to figure out which atoms are connected to which. When there are 3 different elements, as in nitric acid, the element written in the middle is usually the one in the center of the molecule. So in our case, that's nitrogen. Next, if there are oxygens at the end of the formula, they're each bonded to the central atom. So each of the 3 oxygens in nitric acid are bonded to the nitrogen in the middle. Last, when we have an acid, the hydrogen is attached to an oxygen if there is one. So now we know how the atoms are connected in nitric acid. Notice that we've made a total of 4 bonds. As we saw in the previous video, every bond is made of 2 valence electrons. So far we've used up 8 of our 24 valence electrons. Let's keep track of how many are left. In this case, we still have 16. Now let's move on to the second molecule. When you have just 2 elements in a formula, atoms of the first element are the ones in the center, and atoms of the second element are attached to them. So in this molecule, there are 2 carbons in the middle, and 2 hydrogens are attached to them. In the third molecule, the nitrogen is in the center, and the 4 hydrogens are attached to it. And in the fourth molecule, the carbon is in the center, and the oxygens are bonded to it. So far, we've used 6 valence electrons in the second molecule, 8 electrons in the third, and 6 electrons in the last one. That means there are still 4 electrons to go in the second molecule, none in the third molecule, and 18 in the fourth. Now for the third step. If there are any valence electrons left, we add them to the atoms that are attached to the central atom by putting dots on those atoms until they obey the octet rule. So, for example, in nitric acid, this oxygen is attached to the central atom, so we'll add electrons to it. There are 2 electrons in the bond already, so we need to add 6 electrons to it to make it obey the octet rule. We use the rules we already learned for adding dots in the last video, so each side of the atom gets 2 dots. We do the same thing for this oxygen. It has 1 bond already, so it just needs 6 electrons to make it obey the octet rule. And this last oxygen already has 2 bonds, so it just needs 4 dots. Now, what about the hydrogen? Remember, as we saw in the last video, hydrogen doesn't obey the octet rule. Hydrogen only needs 2 electrons, and that's how many it already has, so we don't need to add any dots to it. Now that we did that, we've added 16 dots, so we've used up all the valence electrons that were left for nitric acid. Now we'll do the second molecule. Remember, we don't add dots to the central atoms yet. We're adding dots to the atoms that are attached to the central atom. In this case, that's the hydrogens. And in this molecule, they don't need any dots, so we'll leave this molecule alone. The same is true for this third molecule. The outer atoms are hydrogens, and they don't need any dots. In the last molecule, each oxygen needs 6 electrons, so we'll put 6 on each for a total of 18. That means there are now no more valence electrons remaining. Now for step 4. If there are any valence electrons left, we'll add them to the central atom in order to make it obey the octet rule. The only molecule that still has valence electrons left is the second one, so we'll put those valence electrons on the central atom. In this case, there are 2 central carbons, so we'll just pick one and add the electrons to it so that it obeys the octet rule. So now we're out of valence electrons to add in all 4 of our molecules. But unfortunately, there are still atoms in these molecules that don't obey the octet rule. For example, the nitrogen in nitric acid has 3 bonds for a total of 6 electrons. That can't be right. Remember, atoms are most stable when their valence shells are either completely full or completely empty, and the nitrogen needs 8 electrons to have a full shell. So how do we get 2 more electrons for our nitrogen? That brings us to step 5. If the central atom has fewer than 8 electrons, we'll take an electron pair from one of the outer atoms and convert it into a bond to the central atom. So, in nitric acid, we'll take an electron pair from one of the oxygens and use it to create a second bond to the nitrogen. But there are 3 oxygens. Which one should we choose? Usually, we'll choose an atom that has the most electron pairs. In this case, there are 2 oxygens that have 3 electron pairs, but this one only has 2 pairs, so we won't take a pair from that oxygen. It doesn't matter which of the electron pairs on the other oxygens we pick, so I'll just choose this one. So now we have a double bond between the oxygen and the nitrogen. We saw that a single bond has 2 electrons in it. As you might expect, a double bond has 4. So now our nitrogen has a total of 8 electrons around it, 4 from the double bond and 2 from each of the single bonds, so it now obeys the octet rule. We'll do the same thing for the second molecule. This carbon doesn't obey the octet rule, so we'll convert an electron pair on the other carbon into a double bond. Unfortunately, now that we did that, the second carbon still doesn't obey the octet rule. It still only has 6 electrons. So that means we need to convert the other electron pair into a bond too. That gives us a triple bond between the 2 carbons. A triple bond contains 6 electrons, so now our carbons both finally obey the octet rule. In the third molecule, the nitrogen already obeys the octet rule, so we won't need to do anything to that one. In the last molecule, the carbon only has 6 electrons, so we need to convert an electron pair into a double bond. All 3 oxygens have 3 electron pairs, so we can choose any one we want. I'll pick this one, but any of the electron pairs would be equally correct. So now all the atoms in these molecules obey the octet rule. The last thing we need to do is write the charge on the two molecules that are ions. So this third molecule gets a charge of +1, and the last molecule has a charge of -2. Notice that we put square brackets around the entire Lewis structure and put the charge after that. That lets us know that it's the whole molecule that has the charge and not just one particular atom in it. So that's how we write Lewis structures for larger molecules. You'll get plenty of practice at that in class and in the homeworks and quizzes and tests. You might have noticed that in the nitric acid and the carbonate ion, when we made the double bond, there was more than one oxygen we could have chosen. So, for example, in the nitric acid, I decided to put the double bond between the nitrogen and this oxygen, but it would also have been correct to put the double bond over here. And in the carbonate, we could have chosen any of the 3 oxygens. In reality, when there's more than one equally good choice for our double bond, the double bond actually constantly switches its position between each of the possible locations. It does this very, very quickly, so all of the possible choices occur. This phenomenon is called resonance, and the resulting molecules are called resonance structures. You'll find out in your organic chemistry course that resonance structures are especially important in making molecules more stable. A lot of interesting chemical reactions can only happen because of resonance. Now that you know more about Lewis structures, we can finally understand how this EDTA ion can help save your life if you accidentally swallow plutonium. One thing I didn't do when I drew this ion is I didn't draw the electron pairs. I'll do that now. As you can see, there are a lot of electron pairs in this molecule, and that's the key to why it can get plutonium out of your body. It turns out that the plutonium ion has a charge of +3. It's a positive charge, so all those electron pairs in the EDTA ion are attracted to it. In fact, the whole EDTA ion wraps around the plutonium ion so that the EDTA makes 6 different bonds to the plutonium. Here's what that looks like. In the model on the left, the plutonium is the blue one in the middle, and you can see that it's bonded to 2 nitrogens, which are purple, and 4 oxygens, which are red. Those atoms are where the electron pairs are in the EDTA. So as a result, the plutonium is completely surrounded by the EDTA ion, and that means it can now pass into your bloodstream and get excreted out of your body. The EDTA is called a chelating agent, and chelating agents like this are one way of getting toxic metals, including lead and mercury, out of the body in an emergency. Well, that's it for today. There's still more to learn about Lewis dot structures. In the next video, we'll use them to find the structures of some pretty tricky molecules. So I hope you'll join me for that. Until then, have a good week.